Hello, my name is Pavan, and I will be discussing our submission to the Voice Privacy 2020 challenge titled Adjustable Deterministic Pseudonymization of Speech. The outline of the talk is going to be an introduction and what we proposed to anonymize speech, results and analysis, followed by the proposed intelligibility measurement approach, and followed by conclusion. So the task is given a few utterances and their speaker labels and their transcriptions. We want to modify them such that we want to hide the speaker identity and the spoken message is still clear. So that means we need to change it such that if it were recorded by an unknown speaker, but the same message. So in this task, the evaluation is in terms of automatic speaker verification and automatic speech recognition, and followed by a few subjective tests. So the evaluation plan more concretely is like this. So we have a few utterances. For example, let's say there are N1 utterances belonging to a speaker A and N2 utterances belong to the same speaker, but we've separated them so that when we are presenting it to a speaker verification system, we have an enrollment set as the set of N1 utterances, and we make a system out of these enrollment utterances, and then we evaluate the rest in two utterances. So we get a score which is usually an equal error rate or CLLR score. Also in the evaluation of ASR, speech recognition, we give all these utterances to the ASR system and get a word error rate. So what we require to do is to anonymize the utterances N1 of the speaker to another speaker, which is X, and also anonymize the utterances N2 of the same speaker to a different speaker Y, such that we have the modified data set with which, if we perform these speaker verification, the equal error rate is going to be very high because the enrollment and evaluation set now belongs to two different speakers. But whereas the ASR needs to be as low as possible and as close as possible to the original word error rate. So the challenge provided two baselines. One of them is using neural source filtering approach, where they use feature representations from the original speech and many other features and try to recreate a different speaker. So basically the target speaker is chosen from a reference pool, and we would like the test speaker to sound like one of the reference speakers which we have chosen from the pool. The other alternative is to use signal processing based method, which alters the spectral properties of the evaluation signal. We process at a frame level. So for each frame, we estimate the spectral peaks using linear prediction. So this estimates the formant frequencies as well as the fundamental frequency at the pole locations or at the peaks. So what this method does is it shifts them by a constant factor and resynthesizes each frame. So we get such frames and we overlap add to get the anonymized utterance. So this method is called McAdams method, and the previous method, which uses source filtering method, we've abbreviated as NSF. So we'll be using them later in the results. So what is the proposed approach? So basically what we also do similar to the McAdams method is to simulate a different vocal tract, so how we approach this is in twofold. One is we change the playback speed so that the entire spectrum in the frequency domain shifts by a linear factor. And then the second step is to estimate the formant locations. And so what we do is we would like to shift them using bandpass filters to the desired locations. So how do we get the desired locations is by having a reference speaker in mind. So once we've set a reference speaker to which we would like to anonymize it to, we compute the parameters of the reference speaker. We basically take the mean values of the formant frequencies of the reference speaker, and we also take the mean values of the formant frequencies of the current speaker, and we get the offsets, and then we use the offsets to actually shift the formants at short time level. So the other thing which we also do is to alter the speaking rate and the fundamental frequency F0. So the speaking rate is estimated automatically by locating the syllables. So basically, each syllable is contains a low energy region followed by a burst of energy followed by another low energy region. So these are detected, and then by detecting them, we can also estimate how fast the speaker is speaking. Uh, so basically, it's a well-known technique called pitch synchronous overlap add method, where we can change the fundamental frequency and also overlap add to get a different duration. We also do additional processing using these band pass filters. We can also exchange the F4 and F5 bands. So we also do this, and what we also did was to replace the F5 to F9 bands by a modulated pink noise such that the speaker is not recognizable. Apart from the replacing F5 to F9 bands and also the overlap add method, everything else is deterministic and everything else is reversible. So most of these steps are reversible. We call it a pseudonymization method. So by this, that's why we title it as pseudonymization, because we can actually get back the original speech in the original speaker's voice if required. So more details about this can be found in the paper which is online. So in the experimental setup, we have evaluation data which consists of subsets of VCTK and Libri speech corpora. And we also have a pool of reference speakers to which we can anonymize to. And this is a non-overlapping subset of Libri speech. Non-overlapping meaning it does not overlap with the evaluation data in terms of both utterances and the speakers. The implementation is publicly available. The implementation is purely from Dr. Rob, and it is based on Brad. So I just want to give a comparison of how the reference speakers are selected. So in the neural source filtering model in method, one of the farthest speakers in the feature space is selected to as a reference for anonymization. So the nearness or farness is based on PLDA affinity score. In the McAdams method, there's a constant factor that we just multiply to the spectrums or to the poles of the spectrum. So there's nothing which we take as reference. And in the proposed approach, what we do is we randomly pick one of the reference speakers as the pseudonymized speaker. And the speaker verification and automatic speech recognition models have been provided by the challenge organizers. So if we look at the results, we have the equal error rate of the original utterances in blue. What we want is after this anonymization, we would like the system to fail as much as possible. So the error should be as high as possible. So if we see, the best performing model is the neural source filtering model. But then McAdams method is clearly inferior to the NSF method. But whereas the proposed method, which is based on signal processing, is definitely better than the McAdams method in all the cases. So that's one good thing. And since it is a signal processing method, I think it is fair to compare with McAdams method. And in terms of speech recognition, what we require is that the word error rate remains low after anonymization, and so that the spoken message is clear. So what we see here is, again, the NSF method is still little worse than the original. That means the NSF method does not preserve all the information that is required for speech recognition. And the McAdams method is still worse. But we can see that the proposed method is definitely better than McAdams method in all the cases. And sometimes it's comparable, especially in Libri speech, it is better than NSF method. But in VCTK, it is comparable or slightly worse. So we can listen to a few examples of how each of these anonymization methods sounds. So the first is the original.
The company still had the confidence of its bankers, he said.
The NSF method.
The company still had the confidence of its bankers, he said.
So it sounds a little robotic, as we can expect from any source filtering based synthesizer. So the McAdams method is.
The company still had the confidence of its bankers, he said.
And the proposed.
The company still had the confidence of its bankers, he said.
So what we can perceive is that the proposed method sounds more realistic and probably in more natural, sounds more natural like a human than the other methods. But it's just one data point. So we can listen to another one.
This is a scheme that has a lot of potential.
This is a scheme that has a lot of potential.
This is a scheme that has a lot of potential.
This is a scheme that has a lot of potential.
So what we did here was to track the formant contours on many utterances, but this is an example that we have shown. We've compared the NSF versus the proposed method. So what we can see here is that the proposed method has better formant contours that closely match with the original than the NSF method. And we have shown in the paper that it is quantitative. It's not just one example. So if you want to see more details, please go and look at the paper. Speech recognizers are probably not the best to evaluate the spoken content, especially in these scenarios, because they could be affected by factors such as the language model and the lexicon. So what we instead want to do is we can make use of the original speech and then measure the phoneme level deviation after the anonymization. So here is a block diagram of what we wanted to do. So basically, we have a reference utterance, which is original utterance, and the test utterance, which is anonymized utterance. And what we do is we pass it to a neural network. We pass the feature representations through the neural network to get phoneme posterior probabilities. So Y's and Z's are sequences of phoneme posterior probabilities. And what we want to do is to compute a distance between them using dynamic time warping, which is DTW. So this is a standard DTW based on Kullback-Leibler divergence between each Y and each Z. And what we have done here is to allow transitions which are like self transitions, whereas the transition to the next state and also the transition, a skip transition to the second state, because the durations are not normalized. So what we wanted to do was we wanted to account for the duration of the reference, which is being less than the duration of the test utterance. So when we do this, we get a final score, which is the final DTW distance between the reference utterance and the test utterance in terms of their phoneme level deviations. And so it was already proposed that this one, so this score is a measure of intelligibility, where a lower distance means a higher intelligibility. The proposed method is very much comparable in terms of the DTW distances with the neural source filtering based approach. So in conclusion, we proposed a signal processing based approach for anonymizing speech. It is based on modifying formants, modifying the fundamental frequency, and modifying the speaking rate deterministically. It performs better than the McAdams approach, which was one of the baselines, at both the speaker verification and speech recognition levels. And the method performs comparable to the source filtering based approach in terms of intelligibility. The only thing is that it still needs to be better in terms of speaker verification. And we've also shown that the proposed method is better in tracking formant contours than the source filtering based method. We also investigated the use of an intelligibility measure based on DTW distances between the phone posterior probabilities to compare how well the anonymized speech retains the spoken content. And it also sounds more natural than the source filtering model, and it could be further evaluated actually. So the current challenge focuses only on the speaker verification and speech recognition challenges, but we could also question in terms of whether the output speech is natural or in terms of its quality, etc. And from what we have perceived, it sounds more natural than the source filtering based method, and it could be further a future direction. Thank you.